This is the E-Plane team's final presentation. My name is Thomas Castleman. My other teammates are Devin Ramsey, Brock Lauer, and Patrick Kruger. The objective of the E-Plane team is to design a single-seat, multi-engine, home-built, battery-powered aircraft using composite materials and operating within the 14 Code of Federal Regulations, Section 91.319, that is, experimental aircraft, that will explore the feasibility of electric aircraft. Experimental aircraft means that we do not have to use certified aircraft parts. This gives us a lot more freedom in design, but as the regulation requires, you have to have the words experimental in large letters visible for everybody to see because it is an experiment. We did start to build a scale model prototype, but we didn't finish due to the pandemic, and we won't be talking about that much today. One of the biggest challenges our team faced is that none of us had an education in aircraft design. So we consulted aerospace engineering textbooks directly. From this, we've broken down our work into 12 steps. This isn't the only way to design a plane, but this is the way that we took it. So step one is to define specifications and identify constraints. We researched similar aircraft. On the left, we have a Quickie Q1. This is a single-seat composite-built airplane that cruises over 100 miles per hour on 18 horsepower. On the right is a world record breaker, the Cree. It weighs 139 pounds, cruises at 120 miles per hour on two 15 horsepower motors. Based on the performance of other aircraft, we can start to write specifications for our aircraft. We start with a wide range of numbers, and after some analysis, we narrow these numbers down. On the left are our specifications that we have narrowed down. I've highlighted in yellow some of the important speeds that are used for calculating some other parameters of the design. Our constraints are home built, means we need to have relatively simple construction. It's electric powered and has minimal software required for flight, which means it needs to be inherently stable. The second step is to calculate an estimate for the aircraft weight. We use a sizing equation that is derived from statistical data. It's important to note that our fuel fraction, which is the final term in the denominator, is equal to 0 because our batteries don't lose weight as they use energy. From this, we calculated a weight range of 635 to 670 pounds, and our final weight did come out to be on the end of that at 670 pounds. The next step is to calculate power loading. Power loading is an important parameter that defines aircraft performance. It's the total weight of the aircraft over the total horsepower. We have an equation based on our design type, and we use our chosen maximum speed of 120 knots to calculate a power loading of 13.4 pounds per horsepower. Using the highest weight estimate and our power loading estimate, we can calculate the power requirement to make this plane fly. We can also pick a possible motor from this. We estimated that we needed 50 horsepower, and we chose 4 LU-15 motors at 13.3 horsepower each, giving us a total of 53.3 horsepower. We can also determine our propeller diameter from that, and we determine that it is 42 inches. The next step is to calculate wing loading. Wing loading is one of the most important parameters of aircraft design. Lower numbers represent slower, lighter aircraft, and higher numbers represent heavier, faster aircraft. We use the stall speed that we chose earlier, and we estimate a coefficient of lift of 1.5, which we will check with our airfoil data later. We use a variation of the lift equation to estimate a wing loading of 7.1 pounds per foot square. From there, we can determine wing geometry. Using our empty weight estimate and our wing loading estimate, we can determine wing area. We choose an aspect ratio. Aspect ratio is the wingspan over the average chord, or length over width in layman's terms. We chose 14 because we want to maximize the efficiency of our batteries. This is a generally higher number compared to general aviation aircraft. We estimate our wingspan based on the wing area and our chosen aspect ratio. We estimate a wingspan of 35.8 feet. The next step is to select an airfoil. This is one of the most important steps because the airfoil is one of the biggest factors in determining flight characteristics. Using our chosen cruise speed earlier, we calculate the cruise lift coefficient, and you can see on the red line that our cruise lift coefficient comes at the peak of the lift to drag ratio, which means that we've chosen the optimal airfoil. We can also find our maximum cruise lift coefficient from this graph, and we bring that back into our estimate earlier. We can calculate fuselage length with the equation based on statistical data and the empty weight of the aircraft. Using this, we calculated that our fuselage length should be 16 feet. This is a starting estimate, and the detailed components will determine the actual length. Now that we've calculated many of the parameters that determine the aircraft design, we can draw a sketch. The sketch that you see here is about our 4th iteration. We don't have enough time to go over the rest of the iterations and why they didn't work, but the biggest feature you can see is a biplane design using a closed wing structure. The closed wing increases our aerodynamic efficiency and our structural efficiency. Step 10 is to calculate tail size. The reason we do that is to make sure that we can create enough moment to keep the aircraft stable in flight on the horizontal and vertical axes. When we first did these calculations, we determined that the tail area was very large, so that we either needed to increase the tail area or increase the length of the tail to increase the moment. That was the last major redesign that we did of this aircraft. The next step is to add structure. We want to add stiffeners where the loads are high. In our case, the main forces are going to be the weight of the aircraft coming through the landing gear and the lift generated from the wings coming through the structure into the fuselage. We want to avoid high load concentrations with composite structure. We do this by making a smooth design without sharp edges and smooth curves that can disperse the load evenly throughout the structure. It's difficult for us to analyze composite structure because our tools don't allow us to analyze foam and fiberglass composites. The final step is to analyze and optimize the design. We start by making rough estimates of things like weight and performance. Since we've drawn a sketch, we can start using our CAD tools to create the actual components and get more detailed weight estimates. We can also further refine the rest of our estimates, which will change other numbers. It's a circular process that can be repeated many times, and we still could keep optimizing this aircraft.
The first two control systems we looked at were the elevator and the rudder. The elevator controls the pitch, which is the up and down motion of the plane. We originally wanted to use push rods for the whole system, but found that having rods that long was a safety hazard due to the possible vibrations. So we went with a pulley and cable system in combination with smaller push rods, as can be seen from the figure. The pulleys will be around 10 feet in reality, but 10 feet apart in reality, but for the animation we moved them a lot closer so you can see everything. The rudder system is really simple. It controls the yaw, which is the left and right motion. We use foot pedals and cables that reach back all the way to either side of the rudder. When the right foot pedal is pushed forward, the cable pulls the rudder and the plane turns right. It's pretty simple. The hardest system model was the aileron system. The ailerons are responsible for the roll motion of the plane. As you can see from the animation, the system uses a torque tube connected to the joystick. As a torque tube turns one way, the aileron on that side will go up and the opposite will go down. This gives the roll motion that most of you are probably familiar with.
We used ANSYS Fluent to do airfoil interference testing. We used the CFD software to develop the placement of the wings. We concluded that the bottom wing being shifted aft helped with the overall performance of the aircraft, and it was a comparison between the top wing being aft and the bottom wing being aft. ANSYS was also used to evolve the design of the battery cooling system. It was deemed that angling the cooling system up while flowing the airflow from the bottom to the top instead of from the front to the back proved to be an overall flat upgrade with better cooling capacity, less drag, and improved space efficiency.
For our selected battery, we decided to go with the Samsung 30Q. We looked at a bunch of different options, but they were too sketchy and unreliable, so we didn't really want to do something that could actually just blow up on us, so we chose for a more reliable battery in the Samsung 30Q. Basically, it gives us a voltage of 3.6 volts, 15 amp discharge rating, capacity of 3,000 milliamps, weighs only 48.5 grams each, and costs around $450 per battery. And this is a BOM of all the electronic parts in the plane. As you can see here, we have our Samsung 30Q batteries, a BMS, which is a battery management system, ESC, electronic speed controller, wire size number 1 for the American wire gauge, wire size number 14, and our Luminaire motors. If we look at all this combined together, the initial build for a electric plane is rather expensive. As you see, just the electrical components cost roughly $17,620. But the advantage of having a plane like this is the fact that it's a one-time buy. You don't have to keep refilling on gas or anything like that. So that is the one good thing that this expensive build does have. As you can see, this is our battery configuration. It is a 16 batteries in series, 10 in parallel, that are all hooked up to one BMS. The BMS monitors the system and makes sure nothing over discharges or overcharges. It prevents fires and stuff like that. So this will also be in parallel with 3 other BMSs, which will connect to a single ESC and then connect to a single motor. So there will be 4 setups like this, which encompass roughly 19-20 batteries in total. One of the main problems we had when trying to figure out how to power our motor was to figure out how many batteries we needed, and so we decided on the 16 in series, 10 in parallel configuration. 16 in series gives us enough volts, the 10 in parallel is what gives us our capacity. So once we combine our entire circuit together, we get roughly a capacity of 90,000 milliamp hours. So doing a little bit of math, we can see our respective flight time is 90,000 milliamp hours over 171,000 milliamps, which is how much amps the motor is outputting, which gives us roughly a 31.58 minute flight time. Now on to modeling the battery pack. So as you can see, we have our first 2 iterations of the battery pack. The main problems we were having with the first iteration was it's too bulky. We wanted it to be able to slide in and slide out and it'd be real fancy like, and it was just too bulky and it's too much of a cumbrance to the whole plane. The second iteration is much smaller, but however it's still heavy, so that's why it's not our final iteration. This is the final design for the battery pack. As you can see, it's been hollowed out on the inside, and that hollowed out area made it a lot lighter, and it also allows for some airflow through the battery pack to help the battery stay a little bit more cool. The battery pack also still features a safety factor of 15, so it's very safe and it's ready to go. Here's the rack design. It's the only iteration of it. Fortunately, we managed to get this one right on the first try, it seems like. It has a safety factor of 13.17. I don't think we can actually shrink it any further than it is right now, so we're kind of happy with what we got. Following the fuselage, we modeled the wings and stabilizers. So basically, the wings were based off of the NACA 2415 airfoil, which we then used a tool called it's called Data Spline in Fusion 360. The first iteration didn't use that tool, so it had too many faces, and it couldn't be analyzed through FEA. And that was a huge problem, so we had to remake them and make them, and as you can see in the bottom pictures, they are much smoother, which allowed it to be analyzed through FEA much easier. So next was the modeling of the landing gear. The landing gear design is you want this arch design, which makes it a rigid spring. Rigid spring basically just makes it easier for the landing gear to hit the ground. It's just a type of landing gear design. And as you can see, the first one is just a semicircular shape, and that one got scrapped immediately. It was just basically a test run. And the second one is more or less that arch shape we're looking for, but it was too tall. So then we remodeled to the third one, in which it's a bit shorter and it fits the plane better, and it pushes the plane roughly 2 to 3 feet off the ground, and it's safe, as you can see through the FEA. This is the model of the front landing gear. So the front landing gear is going to be a 6061 aluminum rod that connects to the actual landing gear itself. But this landing gear is in a rigid axle configuration. This configuration means a compressive force goes straight down onto the rod, so it has to be tested for buckling. And we determined that this type of rod should be able to handle up to 1730.58 pounds of compressive force, which is much greater than the expected max weight of the plane. And finally, the overall assembly of all the exterior components on the plane. As you can see, the model looks nice and smooth and it's cleaned up. The prior model had a ton of issues and struggled to run an FEA, but this one fortunately does run an FEA. And as you can see from the force analysis, that is the expected stress that we're going to get. So the thing with this is, though, we have a composite material is what the plane's going to be made out of, but you can't model that in Fusion and test that in Fusion. So we're just looking at what the stress kind of will look like. And in order to prevent too much stress at the root of the wings of the plane, we're making a fillet radius to connect to the plane and add a little bit more structure to sturdy it up a bit.
So some conclusions we reached. So it is possible to design an aircraft that can be powered by batteries. You can get some range. We got 30 minutes. There are some that can fly for over an hour, but it's still generally too heavy for practical aircraft use. Batteries generally are not currently economically practical when you compare to liquid fuels. You generally just can get more range, more performance when compared to batteries. The good thing about batteries is that you pay your fuel costs up front. You will buy a very expensive battery, but it will not cost you very much to recharge. In the future, though, we do predict, and many economists and futurists predict, that development of batteries will enable more practical aircraft designs. Another conclusion we reached, that composite construction is ideal for experimental aircraft, but it's difficult to get certified. Thank you for watching the E-Plane's final presentation.